Section 11.3. The integral test and estimates of sums. Suppose f is a continuous positive decreasing function on the interval from 1 to infinity, and an can be written as a function fn, so there's a corresponding function to each term an. Then the series, the sum of all these ans, is convergent if and only if the improper integral from 1 to infinity of f of x dx is convergent. In other words, if our integral is convergent, then our sum is convergent. If our integral is divergent, then our sum is divergent. So let's prove this. We have first case where the integral is convergent. So we draw our function that corresponds to our ans, and we put rectangles underneath the function. So what we do is we make each rectangle have a width of 1. So underneath each of these left and right parts of the rectangle, these are all integers. And that means that if we want the area of each of these rectangles, then the area is just the height of the curve times the width of the rectangle. So the height of the curve, well, we're doing some right rectangles. So that means that the height will be the value of the function at the integer on the right side of the rectangle. So that means that for the first rectangle, we're looking at the right side, which will be at 2. The second integral will be at 3, the fourth at 4, and so on. So that means that this rectangle has an area of the value of the function at 2, which is a2, times the width, which is 1, so it's just an area of a2. And the next one has an area of a3, an area of a4, an area of a5, and so on. So that means that if we add up all of these areas, then we get the sum of all of these AIs starting at 2. So that must be less than or equal to the area underneath the curve, which is the entire area, because look at all these gaps in between. So that area underneath the curve from 1 to n must be even smaller than if we went on forever. So the integral from 1 to n is smaller than the integral from 1 to infinity, so that means that we have this sum from 2 to n smaller than the integral from 1 to infinity. And this is all, predicated on the fact that f of x is greater than or equal to 0, and that we have a decreasing continuous function. Notice if this function was not going down, then we wouldn't have this underestimate for rectangles, so we wouldn't have this inequality at all. So then we can write that the sum of the partial sum in general is equal to everything from 2 on, as long as we just add that initial term that we didn't have. So that must be equal to the integral plus that initial term. We basically just add a 1 to both sides of this inequality over here. So this a1 plus our integral, because our integral is convergent, it equals some number. So we take that number, we add it to a1, we get some other finite number, so let's just name that number m. So it means Sn is bounded by m for all n. So our sequence is bounded above. But we also know that Sn plus 1, which is Sn plus our next term, is greater than or equal to Sn, since our an plus 1 term is Fn plus 1, which is also greater than or equal to 0. So we have a increasing sequence, and it's bounded, so it must be convergent by the monotonic sequence theorem. So as a quick example of this, how about we take a look at the possibility that f of x was 1 over x squared. So then this first rectangle has an area of the y value 1 over 2 squared, because over here is f of 2. And remember, the width is 2 minus 1, which is 1, so multiplying the y value by 1 doesn't change it. The next rectangle would have an area of 1 over 3 squared. Then we'd have an area of 1 over 4 squared, and so on. So if we take the sum of all of these areas, then we get an under approximation for the area underneath the curve. So it makes sense that adding up 1 over 2 squared, 1 over 3 squared, 1 over 4 squared, that should all be less than the integral from 1 to infinity. So if we took 1 over 1 squared, our only missing term in the series of 1 over n squared, and we added that to our integral from 1 to infinity of 1 over x squared dx, then we would get 1 over 1 squared is 1. And then this integral we calculated in section 7.8, we saw that it converges, and it's also equal to 1, so then this would be 2. So that would be the entire area underneath the curve, plus the first term that we didn't put. So that means that the sum for n equals 1 to infinity of 1 over n squared should be less than 2, because the sum is just the rectangles without all these gaps. So that must be less than the integral plus the first term. Notice that this does not give you the value of the series. It only tells you that the series converges. If you actually wanted the value of the series, you'd have to do something a lot more complicated. In this case, the sum of 1 over n squared is actually pi squared over 6, and it's not easy to compute. So the only thing the integral test can tell you, provided that you have a suitable function, is whether or not the series converges or diverges. Notice that when we did the sum of 1 over n, the harmonic series, it actually diverged, and that actually corresponds to the integral 1 over x diverging. But let's finish up this proof over here. The other case is that their integral is divergent. So in that case, our integral from 1 to n goes to infinity as n goes to infinity. Using our bottom figure, what we do now is we take rectangles on the left side, which will be an overestimate for the area underneath the curve. Notice if we take them at the left side, then our first one starts at 1 instead of starting at 2. So we immediately get that a1 through an minus 1 is greater than or equal to this integral from 1 to n of x dx. So that means that our partial sum up to n minus 1 already diverges to infinity. So of course adding the next term, that an, to complete it and give you Sn, is definitely going to cause it to diverge also, which makes it even worse. So as an example, what we could do is take a look at, we already looked at 1 over n, so how about we look at 1 over square root of x. So in that case, our first rectangle has an area of 1 over square root of 1. Then we get 1 over square root of 2. Then we get 1 over square root of 3, and so on. So all of these rectangles over-approximate the area of the curve. We know that the integral from 1 to infinity of 1 over the square root of x dx diverges, as we saw in section 7.8. So that means that our sum from 1 to infinity of 1 over square root of n must diverge as well, because it's even bigger. So notice that in order to use the integral test, you need quite a few conditions. You need a continuous function, you need a positive function, and it needs to be decreasing, and you need a function that corresponds to all of your ans. So we can relax this a little bit at least by saying that the function does not actually have to be always decreasing. It just has to be ultimately decreasing. In other words, my function could do something insane as long as it levels off towards the end. So, and of course it has to stay continuous. So instead of saying that it needs to be decreasing on 1 to infinity, I could use any number past 1 as well. This follows from the fact that we talked about in the previous section, where if you have a bunch of finite terms in a series, those finite terms at the beginning of the series don't really matter so much. They don't really affect the convergence of the series. If your series converges after a certain number, then it'll converge if you throw in a couple extra numbers. It'll change the value, but it won't affect the convergence or divergence. So we'll do a couple examples where we start a little bit past 1 with decreasing functions. let's start by testing the series 1 over n squared plus 1 for convergence or divergence. So we need a corresponding function. Let's look at f of x equals 1 over x squared plus 1. Well, that's definitely continuous, positive because of the square, and because we're starting at 1, and it's decreasing, provided that we are on the interval from 1 to infinity. So let's also take a look at our integral. We need our other condition where something happens to our integral. And we'll take a look at 1 over x squared plus 1 dx as we integrate from 1 to infinity. So remember that for improper integrals, we're taking the limit as some other variable goes to infinity, where we insert that variable instead of infinity. So we take our antiderivative. So that's going to be the inverse of tangent. Because 1 over 1 plus x squared is arctangent when you take the antiderivative. So that means that we're taking the limit of tan inverse of t minus tan inverse of 1, which is pi over 4. Okay, so remember, as t goes to infinity for tan inverse of t, we hit an asymptote at pi over 2. So this limit is pi over 2 minus pi over 4, which is pi over 4. So our integral converges. So since our integral converged, that implies that the sum of 1 over n squared plus 1 also converges. And it's convergent by the integral test. Remember, we did not get the value of the series. We only saw that we could get the value of the series, hopefully, potentially, using some other method. Let's see if we can figure out what values of p make the p series convergent. P series is just 1 over n to the p summed up. So let's split it up into different values of p. Notice that if p is negative, then we're looking at the limit of 1 over n to the p, and that's infinity. The only reason I'm looking at the limit of 1 over n to the p instead of the limit of the entire partial sum is that we have a test for divergence, or an nth term test, which says that if the limit of the sequence is not 0, then you can't even bother to try to even take any kind of sum. It's not going to happen. Your sequence has to level off, and if you want to be able to add anything up. So let's look at p equals 0 now. We have the exact same thing. Our limit of 1 over n to the p becomes the limit of 1 over n to the 0, which is 1. So in both of these cases, our sum diverges by the test for divergence. Notice in the first case, putting a negative value for p is the same thing as really just summing up n to the p, because it's in the denominator, it moves it to the numerator. And summing up n, to some power over and over and over again, there's no way that could possibly converge. So we saw negative values of p, we saw 0 value of p. How about we see positive values of p? So if p is positive, then we're going to look at the matching function or corresponding function 1 over x to the p. And that's continuous. positive and decreasing along our interval from 1 to infinity. And if we take a look at our integral of 1 over x to the p, then we know that that converges if p is greater than 1, and it diverges if p is less than or equal to 1, as we saw in section 7.8, example 2. So this means that our sum, 1 over n to the p, converges if p is greater than 1, and diverges if p is between 0 and 1. Notice if p equals 1, we get the harmonic series. And this is all by the integral test. So we have another kind of proof that the harmonic series diverges. So that means that we only converge if p is greater than 1, because we already saw that it diverges in the other cases by the test for divergence. So how about we summarize all of this by saying that our p series, 1 over n to the p, is convergent if p is greater than 1, and divergent if p is less than or equal to 1. Let's use what we just proved to see if a couple series converge or diverge. Notice 1 over n cubed, that's just a p series with p equals 3, which is bigger than 1. So our series converges. Notice that 1 over a cube root of n is just 1 over n to the 1/3 power. So that's also a p series. In this case, p is equal to 1/3, which is smaller than 1. So that means that the series diverges because it's a divergent p series. How about the series ln n over n? Well, we have a corresponding function, f of x equals ln x over x, and that's positive, and it's continuous for all x values bigger than 1. However, we don't know if this thing's decreasing at the moment, because it's just not so obvious with the ln x over x. So when we want to know if a function is decreasing, we can look at the derivative. So the derivative can be obtained using the quotient rule. We get 1 over x times x, taking derivative of ln x, throwing in x, and then minus ln of x times the derivative of x, which is 1. We divide by x squared. We get 1 minus ln x over x squared. So that means that this will always be positive, so we only have danger when this thing is bigger than 1. So that means that our derivative will be negative when ln x is greater than 1, which is when x is greater than e. Just take both sides, raise them to e. So that means that f is decreasing when x is greater than e. So we also have that our integral from 1 to infinity of ln x over x dx is equal to the limit of the integral from 1 to t of ln x over x, and taking the antiderivative we get ln x squared over 2 from 1 to t. So that's just the limit of ln of t squared over 2. And as t goes to infinity, ln goes to infinity, so our integral is divergent. So since our integral diverges and everything meets up for the criteria for our integral test, we have that the sum of ln over n diverges by the integral test. The remainder, s minus Sn, which is the sum of our series minus the partial sum, is basically everything that you have left over if you were to stop somewhere. Let's say add up the first 10 terms, then every term after 10 in our infinite series would be the remainder. So our remainder tells us how far off we are from our actual sum if we use a partial sum to estimate it. So we have a theorem that the remainder is bounded by these two integrals, provided that, of course, we meet all these criteria for our integral test as continuous, positive, and decreasing. So this should sort of make sense, because if we take a look at the integral, then our remainder is just all of these rectangles where we start at n. So there's obviously a whole bunch of other stuff over here that we haven't looked at, that we've already, taken as our sum. So this is everything left. Well, by our picture, we can see that everything left is going to be n plus 1 all the way on to infinity. That's just the integral from n to infinity. So it should make sense that this is our remainder, and it is smaller than the value of the integral. Doing the same trick that we did when we proved the integral test, we can take rectangles on the left side and start at n plus 1, and then we'll see that all of these rectangles are also our remainder, and they are bigger than the integral, provided that we move the integral down to start at n plus 1 instead. So that makes sense that our remainder will be sandwiched in between these two integrals. Let's approximate the sum of the series 1 over n cubed by using the sum of the first 10 terms, and then we can estimate the error involved using our error test. So in order to do this, we're going to need the integral at some point from n to infinity, so we might as well compute that. So that's the limit of the integral from 1 over x cubed, so taking the antiderivative, we just get minus 1 over 2x squared, and we evaluate that from n to t. I'm basically just skipping the step here where I replace infinity with t and then jump straight to the antiderivative. So that's just the limit of minus 1 over 2t squared plus 1 over 2n squared, which is 1 over 2n squared. So let's take a look at our sum now. Well, that's 1 over n cubed, and we want to approximate that using a partial sum up to 10 terms. So that'll be 1 over 1 cubed plus 1 over 2 cubed plus 1 over 3 cubed, and so on until I've added up the first 10 terms. plugging that into our calculator, we get approximately 1.1975. So this means that our error estimate should be less than or equal to the integral from 10 to infinity of 1 over x cubed. And as we saw, the integral from n to infinity is just 1 over 2n squared. So that means that this error is going to be at most 1 over 2 times 10 squared, which is 1 over 200. So this implies that our error is at most 0.005. What if we wanted to make our error even smaller? How many terms would we need to have to ensure that the sum is accurate to within 0.0005? So this means that we want Rn, which is less than or equal to the integral from n to infinity of 1 over x cubed, which we saw as 1 over 2n squared, to be less than 0.0005, which is the same as saying that n squared should be greater than 1 over 0.01, which is 1,000. So that means that n should be greater than the square root of 1,000, which is about 31.6. So it looks like we need 32 terms to be on the safe side. This leads us to our next sort of theorem, which we'll call a corollary, that if f of k is ak, where f is a positive continuous decreasing function, notice we're using k because we're already using n, then if we just take this estimate over here that we had, remember, Rn is s minus Sn. So if I just take s and add it to all three sides, then I end up with s by itself over here. I end up with an Sn on the left and an Sn on the right. So that gives us this corollary right off the bat. Now we have an integral estimate for our sum of our series. So instead of just estimating a series by cutting off after a certain number of terms and adding up a partial sum, we can estimate a series using a partial sum added to an integral. So as an example of that, we'll estimate the sum of 1 over n cubed with n equals 10 using this corollary. So we have s10 plus the integral from n plus 1 to infinity, so that's 11 to infinity of 1 over x cubed dx. That must be less than or equal to the actual sum of the series, which is less than or equal to s10 plus the integral from 10 to infinity of 1 over x cubed. So we already know that the integral from n to infinity of 1 over x cubed is 1 over 2n squared. So that means that s10 plus 1 over 2 times 11 squared is less than or equal to s, which is less than or equal to s10 plus 1 over 2 times 10 squared. As we saw before, our sum of our first 10 terms is about 1.197532. Just go a couple more decimal places. And that means that we have s10 plus 1 over 2 times 11 squared is 1.201664. And our other estimate is 1.202532. So if we take the middle of this interval and use that as our estimate, then we can say that the sum of 1 over n cubed is about 1.2021. Since we're in the middle of our interval, that means that we're halfway between the left and the right. So if we take the width of the interval and divide it by 2, then we see our maximum error is less than 0.0005. Notice that in order to get to this amount of error, this accuracy before, when we were just estimating our sum using a partial sum, we needed 32 terms. Whereas when we estimated our sum using a partial sum and an integral, we only needed 10 terms. So this approximation is much more accurate.